All right, chemistry class, we are nearing the end. You guys are doing great. You're working hard, you're getting all your stuff turned in, and I really appreciate this. We know we have this AP test coming up on the 14th. So when you go to the AP website and you're trying to find, accurate dates, I know right now, the last time I checked, when you show up on the site, the very first day dates that are up there are actually the old dates. You need to click COVID adjustments, and it talks about how the tests have been moved back a little bit. So basically what we're doing today is we're finishing up, or getting close to finishing up, the last little bits of information that we need. We're going to be talking about some solids and the types of attractive forces that the solids have. So we still need to talk about a few things like allotropes and alloys and metallic bonding and network covalent bonds. And so we should be able to get through that pretty easy today. After that, really the only things we have left would be chromatography. And so chromatography is going to be working off of the intermolecular forces that we've been discussing so far. So once we've done that, the content that we need for this test, we should have it all locked. And that's going to leave us with about 2 weeks that we can review before this AP test hits us. So that'll be a good thing, and I have some ideas planned on how we can review for some of this, and AP has been producing a lot of links on their sites. The only issue with the AP reviews is their YouTube videos, and every one is like an hour long, and I know that it's tough for you guys to sit through an hour lesson, you poor things. But today we're going to talk about one of the last major topics, then we have a couple chromatography things to talk about, and we'll probably do those next week. And then after that, we're on to review and on to fives for everybody. So I'm still learning a little bit about what is going to be on the exam. And as I find more and more out, I'll integrate that into our reviews. So let's go ahead and switch over to Notability and take a look at some different types of solids and the forces that they have. So here we go, we're taking a look at our solids. We have 3 different types of solids that we are going to be looking at today: ionic solids, molecular solids, and atomic solids. So I have a little slide here showing us the difference in each of these things. So we can see in a ionic solid, this would be something like NaCl. This is something that's going to form a lattice. We've talked about this many times already. We've seen over and over again that you're going to have this alternating Na plus, Cl minus, and then another Cl minus here, and then an Na plus there. You can't have 2 positives next to one another. You can't have 2 negatives next to one another. And so they alternate their charge. Gives us a very organized configuration. We tend to see lots and lots of crystals in situations like that. The next one that we've seen a lot of would be the molecular solid. A molecular solid would be something like ice, and we know that ice can form, or water would be a better way to phrase that. We know that this can form nice organized crystals as well because of our, once again, intermolecular forces. When we're dealing with our intermolecular forces, we're getting a slight negative here, slight positives here, and so there's a certain way that this is going to need to arrange itself. And we get a very organized and ordered pattern. And then the last one is an atomic solid, and we haven't spent a lot of time talking about atomic solids, but one of the more common atomic solids, basically to be an atomic solid, you need to have one atom repeated over and over and over again. And so a common one that everybody likes is diamond. You just have carbons repeated over and over again. But another really more common type of atomic solid would be a lot of our metals, right? You have just copper repeated over and over again, or just iron repeated over and over again, or something along those lines. They don't tend to be 100% pure all the time because they tend to form alloys, and we're going to talk a little bit about alloys in a minute, but they would be another example of an atomic solid. One atom repeated over and over again. And when they're repeating over and over again, we get these organized patterns. We tend to see crystals. So even things like metals, when we look at them, they actually form crystals if you look at them at the atomic level. Now, there are a few things that we would consider to be amorphous. So even though they have the possibility of forming these organized patterns. Sometimes they just don't. Glass is a really good example of that. We have the SiO2. When we look at this picture here, you can see that there's really no exact structure to this. Like, what shape is this, right? That's not any kind of ring that we would recognize. Like, we have a little ring here, we have a big ring here. They're not even perfect rings. And so things like glass and rubber and a lot of plastics, these things are amorphous. There's real no order to their structure. Now, it's not to say that you can't get them with a nice order to it. Glass, for example, you could pay a lot of money and you can get like crystalline quartz glass. And so it is possible, but there are some things that they're just not. So when it comes to these things, like I say, we've spent a lot of time probably on ionic solids and molecular solids. I wanted to take a look at some atomic solids today, the metals. And so when we're looking at our metallic bonding, this is something that we should have got in first year chemistry, but I wanted to quickly review it. Remember that when you're looking at metals, you have your positive nuclei, and we know that these atoms always have electrons that are flowing around them. And the difference with a metal is they're not possessive. What I mean by that is they don't really care which electrons they're holding on to. They don't have to say, this is my electron, it's mine, I'm keeping it, you can't have it. That would be something like an ionic or a covalent bond. In the metallic bond, it says, hey, I don't care what electrons I have as long as I have, say, 10. Right? So if they tend to move around, they're okay with that. We say that their electrons are delocalized. They're not trapped in one spot. So this particular electron might be hanging out with this metal right now. And in 5 minutes, it might have drifted all the way down here. But if it loses this electron, then this electron is probably working its way this way and it's replacing it. And then that one's going to move over here, and then this one's going to move over there, and this one's going to move, right? They don't really care. They're flowing. And so a lot of people describe this as a sea of electrons. The equivalent basically of throwing a water polo ball in the pool. The water polo ball would be the positive nucleus of your metal, and then the water all around it is the electron. So it's completely surrounded by electrons all the time, and so it's happy, or it's fulfilling its octet or whatever it is that it's trying to do to get to the lowest energy state possible. But it doesn't, the water's not trapped directly around the ball. It's going to flow around it. Now, because of this relationship, it gives us a lot of interesting traits when it comes to the metallic bonds. We can see that because of this, they do form crystal structures here. And so they're also going to be able to conduct electricity really, really, really well. Because the electrons are already flowing, they're not locked in place. So we know that in a covalent bond, they never have any charges. The electrons are just stuck and trapped in one place. Charge will never move. They never conduct. But with ionic bonds, we talked about how sometimes they conduct and sometimes they don't. So an ionic bond conducts if it's dissolved in water because you can get those charges moving. It's all about moving charges. And metallic bonds have moving electrons flowing all the time, and so they conduct really, really well. We're also going to see that they're very malleable, ductile. This basically just means that they don't shatter very easily, right? It's kind of like if you walked up to an ionic bond and you have something like this, Na plus Cl minus, Na plus. Okay, and so then we'll fill in our others here. This is the configuration that they like. If you strike it with a hammer right here, and you basically take these things, and when you hit it with that hammer, it gets bumped over a little bit. When this happens, what did we just do? Well, we set these things up right next to each other, and we set these up right next to each other, and they do not want that. They repel, and so basically what's going to happen? Your glass shatters. Now, if you tried to do this with a metallic bond, it'd basically be the equivalent of walking out into the pool and striking the water polo ball with a hammer. What does it do? It just bobs, right? If you were to push two of these, if you push this one over next to this one, what's going to happen? The electrons are just going to flow in between and separate them out. They're going to start to fight. They're going to start to repel. And instead of shattering and actually going to war, the electrons just relieve that stress and that pressure by flowing back in between them. And so we find that they're really hard to shatter. The only way you can really shatter metals easily is if you get them really, 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 really cold, because if you get them cold, the electrons stop flowing. And then they start to act more like ionic bonds. And we know that ionic bonds can be very brittle. So these are some different things. Most of them have high melting points, but there are a few exceptions. Things like gallium and mercury tend to have really low melting points, but most of them have fairly high, and they're all going to be shiny as well. But one of the coolest things about metals is the fact that they can form alloys. And there are some different types of alloys that they can form. But first, what is an alloy? When you take an alloy, basically metals have their strengths, they also have their weaknesses. For example, iron. Iron is an amazing metal. Our whole society and world revolves around iron. It's really tough, it's really flexible, but a downside of iron is that it rusts like crazy. And sometimes iron is actually a little too soft, and we want to maybe stiffen it up, make it a little bit harder. So there are some weaknesses to it. And what we can do is mix that iron with some other elements, and you can save their strengths and remove their weaknesses. And so alloys are basically making materials without their inherent weakness. And so they usually make alloys for things like corrosion. We said the iron rusts. So if we take that iron, and if we look over here, we have something that we call stainless steel. You mix that iron with things like nickel and chromium, and all of a sudden that orange rust that's like a cancer to a car or any piece of steel, it goes away. These things are really resistant to rust. If you take that iron and you add some carbon to it, you make it a lot harder. It doesn't twist and flex as easily, and now you have some modern steel. And so there's different things that we can do. They can actually take things like the iron and the steel, and they can add things like molybdenum to it, and that's what surgical steel is, and it's actually really resistant to bacterial growth. And so there's just a lot of options. Sometimes they don't even do this just for their toughness properties. Sometimes they just do this for decoration. For example, white gold. You know, you buy jewelry that's white gold, and gold is not white, right? So they're adding different chemicals to the gold, or rose gold, for example. Right, so you go to the jewelry store, you get a ring or a watch, and it's in rose gold. It's not just pure gold anymore. What have they done? They've added some carbon to it, or some copper to it. And that copper is going to give it sort of that pink color. And so sometimes they just do it for decoration. But there's two different types of alloys that you can make. There's interstitial and substitutional. And it all comes down to the size. So when we're looking at the size, let's take a quick look at these examples here. You could see that copper and zinc are roughly the same size atoms. And so what you can do is you can pluck one of them out and substitute the other one for it. Okay, so this would be a substitutional. Now, an interstitial, you'll notice that carbon is a much smaller atom than iron is. So plucking one out and replacing it, it's not going to fit right. But what it can do is it fits in the gaps. And what it does is normally these little gaps give us space for some movement. They can wiggle and they can jiggle. But if you stuff carbon atoms in those open spaces, what you do is you take away some of that room to wiggle and jiggle. It's like adding wedges to something. You're wedging these atoms in there and you're tightening up the whole entire structure, and you make it a lot harder. So we have substitutional. So if you're looking at the periodic table, if it's an AP test and they say, what kind of alloy do you think this would form? Look at where the atoms are on the periodic table. If they're sitting right next to each other, they're going to be roughly the same size in terms of diameter and radius, so it's probably going to be a substitutional. If they're really far apart from each other on opposite ends of the periodic table, there's probably a very large size difference, and it's going to be an interstitial alloy. Let's see. So I just put a few different properties that some of these alloys do when you're adding that element. So you add cobalt to something, and it helps make good magnets, or add manganese to get things really, really tough. So these are just a few things. Sometimes they'll add a metal to help it withstand high temperatures, so like things like titanium. So we've got some of these different examples here. The last thing that I wanted to talk about is a network solid. And a network solid is usually covalent, and it's one huge giant molecule. So it's almost always an atomic solid, like carbon is one of the higher ones. And the thing you have to watch out with network solids is they share some properties of ionics and covalence. And so a lot of times you see these questions, they'll say, what kind of bonds do you think a substance has if it has this melting point, this conductivity, etc.? So something like carbon, if you picture diamond, remember diamond is carbon going to 4 other carbons. And then that carbon is going to 4 other carbons. I'm not doing a great job of drawing this, but you guys get the idea, right? It's just this one huge carbon structure of carbons going to carbons, and it's going to be 3-dimensional, and they're all linking together, and it's basically going to give it a very high melting point, right? So this is not like water. When you have water and you want to separate water molecules, so right now let's say it's a solid, these 2 water molecules are stuck together. When you want to separate it, you have to add energy to break bonds. What kind of bonds are you breaking here? You're only breaking, when you melt water, a hydrogen bond. And we know that a hydrogen bond compared to a covalent bond is very, very weak. So if I want to melt a diamond, there are no hydrogen bonds here for me to break. If I want to actually melt this and separate the atoms, what do I actually have to break? I have to break a covalent bond. This is similar to an ionic bond, right? If you are trying to melt this, there we go. If you're trying to melt this, there's no hydrogen bonds here to break. You have to actually break an ionic bond. That's why these things have such high melting points. They're going to share this. They're going to also both form crystals. Now, where's something that's going to be different here? Usually, it's the conductivity, right? This still has charges, and it still has the ability to conduct electricity. But this one, it can't conduct electricity, right? They're shared electrons, and they're in that regard, they're all shared evenly. So this is never going to conduct electricity. So conductivity is still a really good way to separate them out, with one exception. There's always that exception at the AP level, right? And we've talked about this one exception before. I'm telling you that carbon doesn't conduct electricity. But if you think back to your electrochem, right? When we were doing things, when we were doing these batteries, you guys remember our electrolytic cells, right? What did we say we could use for an electrode? If we had a substance that was a gas, you don't have an electrode for it. We always had 2 options. One option, if you had the money, was platinum. But what was the other option? Graphite. And what is graphite? Graphite is actually carbon, right? So let's take a look at how graphite is slightly different than a diamond, so we understand this aspect of conductivity, and then we can stop there. When we're looking at carbon, carbon forms what we call allotropes. Means that when it bonds, it can take on some different shapes. And the main 2 that we see is a diamond and graphite. But there's also these fullerenes, and I'll show you guys that. So when we're looking at carbon, you'll notice the difference here between the carbon is a diamond and then carbon as graphite. In this one, each one of these carbon atoms is going to 1, 2, 3, 4 carbon atoms. The hybridization here is sp3. Ooh, I use that word hybridization. Some of you guys are like freaking out all of a sudden. Remember that each one is got 4 bonds to 4 different elements here. But when we look at a graphite molecule, take a look. You've got this guy going 1, 2, 3 bonds. This is sp2. Where is my other bond? I know that carbon can't have just 3 bonds. There must be a double bond, right? So there's a double bond right here. And then we look at this guy. Well, it's got 1, 2, 3. So it must have a double bond. Maybe it's right here, right? And so all of a sudden, we get something that starts to look like a benzene ring. You remember our benzene rings? We just recently talked about some benzene rings. We know that they have 3 double bonds, right? And does the double bond have to be here? No, it could be here. Does this one have to be here? No, it could be, it could be over here. And this one could be over here. And that's exactly what happens. They tend to move, and we say that they're always flowing in a circle like this. Well, that's exactly what's happening in my graphite. I'm getting these double bonds are moving around. They might not be flowing in a circle, but they're flicking back and forth, right? So maybe you got it here, and then it's here, and then it's here, and then it's here. And so because these things can flick back and forth like that, you have moving electrons. And so graphite, unlike diamonds, can conduct electricity because of the double bond that you have present in it. Now, graphite is also very soft and slippery, because while this sheet right here is very, very hard, it's actually stronger than a diamond itself, because remember, when we add a double bond, you increase the strength of that bond. But it's very, very strong. In the sheet, this is really, really, really hard, very impossible to break. Not impossible, but very difficult to break. But what's holding this sheet together with this sheet? Intermolecular forces, right? And what type of intermolecular forces would graphite have? It's only carbon atoms here, right? We don't have any other atoms thrown in. So what kind of intermolecular forces would this be? London dispersion forces. It's all nonpolar. So you're not having any dipoles, no hydrogen bonds. You don't have any carbonyls popping in here. It's only London dispersion forces. So these are actually fairly weak, which is why when you're writing on the pencil, you can see what's happening. These sheets are just sliding apart. You're not actually breaking the sheet in half. That's never happening here. And so there's actually a lot of research going into these individual sheets because they're so strong, and they're calling it graphene. And they're able to take these things and make really super ultra thin, 1 atom thick sheets, and they conduct electricity, and they're flexible, and they can't be destroyed, and they can weave them into threads and fibers, which are basically stronger than steel. I'll try and to include a little link to something showing you guys a little bit about graphene. It's a pretty neat topic, a pretty neat subject. The only other way you'll see it is a fullerene, and I'm not going to ask you guys really anything on that. I doubt they will either. They call it a buckyball. It's a Buckminster fullerene, and it basically is like a soccer ball. You have 2 different shapes that are integrating together. So we have the 5-sided, and then over here you always have the 6-sided. It's the exact same way. So 1, 2, 3, 4, 5, 6, and then here's the 1, 2, 3, 4, 5. So it's the same type of thing that you see in a soccer ball. And these are pretty indestructible as well. You can squash them down flat. They just pop right back. And they can open them up and make nanotubes and all kinds of cool stuff with that too. But I would really hope you guys understand the difference between graphite and diamond, right? So this is a network covalent material. They're both atomic solids, but this one's a network with the diamond. And then this one technically can be a bit of a network as well, but we have this ability to conduct electricity, which is a little bit different. Normally, a network covalent would not be conducting electricity. All right, so hopefully this wasn't too much for you guys. I'll talk to you soon.